Hello, my name is Yejin Jung, and today I'll be presenting SmartBlink, a real-time AI-driven adaptive pedestrian traffic light system for enhancing perceived pedestrian safety and traffic efficiency. Every year, road traffic collisions are responsible for approximately 1.2 million deaths and up to 50 million injuries. More importantly, 24% more vehicle fatalities occur at intersections. Currently, there's a fixed time signal of crosswalks, which is designated to 1.2 meters per second, according to the U.S. Department of Transportation. However, 96% of adults over 60 and people who have disabilities are slower than this average pedestrian speed, which makes it really hard for them to cross crosswalks in time and often left stranded. This is why I developed SmartBlink. SmartBlink is a first low-cost real-time adaptive traffic system designed to make safer and more inclusive crosswalks that promotes confidence and autonomy for all pedestrians. And here's how I did it. First is a hardware development. I used smartphone, tablet, custom 3D printed tablet case, and two 3-meter tripods to recreate the angle as you can see in this photo. There was an iterative software development for the algorithm. Each version was improving on the previous version, and I used on-device YOLO V11 detection, perspective correction algorithm, as well as signal processing pipeline, all to ensure there's rapid detection and accurate detection of pedestrians' movements. The pedestrian detection system were tested in different lighting conditions to ensure that it will be working at metropolitan and city environments where there's dynamic background conditions. Here's a perceived pedestrian safety model. So whenever SmartBlink is placed, it is able to do a risk evaluation of remaining crosswalk distance versus predicted time of the user and do a TTC evaluation, which is time to crash evaluation, and pedestrian behavior. And on top of that, it takes in the driver vehicle behavior as well, such as distance, braking time and threshold, and lanes. And by taking in all of that information, it gives an adaptive intervention by extending the signal time. It also gives a haptic notification for the driver and the pedestrian simultaneously. Here is a real-time pedestrian detection. So as you can see, all pedestrians and their speed were simultaneously captured with SmartBlink, and the gray bounding boxes are there to ensure privacy. I also did an assisted device annotation. Because the group of people that usually couldn't finish the crosswalk had a high tendency of using assisted devices, such as canes, crutches, I did an additional annotation to ensure that SmartBlink could detect people with and without these assistive devices all accurately, and it showed a very high accuracy, ensuring that SmartBlink can handle different conditions and detect all pedestrians safely. Here's SmartBlink in action. So this a person, according to the current speed, would not have made it in the 16 seconds provided. So SmartBlink interactively added 6 more seconds to make it 22 seconds, and by doing this, the pedestrian didn't have to rush and could take their time and still finish the crossing safely. Here's performance under different conditions. The lane width and lighting conditions were all really high accuracy, and for the lane width specifically, the error decreased by almost half from before the perspective correction algorithm and after the perspective correction algorithm, which means that SmartBlink is very accurate to use in various city environments and lighting conditions as well. And here's perceived pedestrian safety. By using vehicle TTC, such as braking behavior and deceleration rates, I was able to develop these applications for pedestrian mode and driver mode, and it was successfully issued to both the driver and the pedestrian when tested. Here's a traffic efficiency evaluation and cost analysis. It was shown that the average delay was about 0.17 to 3 seconds using the Sumo evaluation, which in the context of a city when deployed is very minimal to the overall traffic flow. Now, the cost evaluation. While the traditional traffic light costs almost $1,700, SmartLink is only $262 by using commercial devices such as phones and smartphones. And this makes it much more affordable for cities and governments to pilot this program before implementing it. Here's my conclusion. Throughout all these processes, I was partnering with the Boston H. Strong Department, the Veronica B. Smith Senior Center, and professors in urban planning to make sure that I was focused and I was continuously receiving feedback to make my project better. Now, what's the impact of this project? Well, it's a next-gen traffic light system for more safe crosswalks for elderly people with limited mobility and young children and caregivers specifically. And it can promote social well-being by enabling social interaction. It also reduces pedestrian vehicle conflicts through real-time multi-agent combination. It's very convenient for local governments to use with high population of seniors. And last but not least, enables underserved communities to use SmartBlink, test this innovative system to make their crosswalks more safe. Thank you so much for this entire presentation.